Double angle identities. Let's take a look at how we can use the sum angle identities that we looked at in the last video to create some formulas and identities for double angle identities. And we'll start off with sine. So since sine A plus B is equal to sine A times cos B plus sine B times cos A, if we make A and B the same, what we're then asking is, what is A plus A, or sine double the angle A, worth? Well, all we have to do is find an expression if we substitute in A for both A and B, and so sine A plus A would be equal to sine A cos A and sine A cos A. These are exactly the same terms, so I have two sine A cos A's. That's what sine doubling the angle will be worth, and that's the first of our double angle identities. Similarly, for cos double angle identity, we can think about that as cos A plus A, and using cos A plus B, which is cos cos minus sine sine, I substitute in A for my B, and I get cos A minus sine A times sine A, which is rewritable as cos squared A. Cos times cos is cos squared, and sine of the same angle is sine squared A, and that's the first of my double angle identities for cos. And I say first because there are a couple other options that I have. If I remember back to my Pythagorean identity, that sine squared A plus cos squared A is equal to 1, I can rearrange this. So I can solve for sine squared A and get 1 minus cos squared A, or I can solve for cos squared A and get 1 minus sine squared A. And depending on which way I rearrange it, I can take my cos double angle identity and I can substitute in for one of these two formulas. So if I substitute in sine squared A as 1 minus cos A, I get something that looks like this, 1 minus cos squared A instead of sine squared A, and that becomes cos squared A minus 1 plus cos squared A, and I get a new double angle identity. Cos squared A plus another cos squared A is 2 cos squared A's minus 1. So there is an alternate way of writing the cos double angle identity that's just in terms of cosine. I can do the exact same thing but do a substitution so that it's only in terms of sine. That's using the other part, this part, and doing a substitution. So let's do that next. So I can start with cos squared A minus sine squared A, and then I can say that's equal to, now cos is getting substituted, 1 minus sine squared A minus another sine squared A, so I can get that cos double angle identity is equal to 1 minus 2 sine squared A's. So I have three different formulas for cos double angle identity. Similarly, I can do this for tan. I'm not going to walk through all the steps for tan, but if you use the formula of tan A plus A and now make it 2A, you get 2 tan A over 1 minus tan squared A. So all of these formulas, and there are 5 of them, are good to know for this section. Commit them to memory, practice using them so that we can actually do some harder, higher level questions with them, and that's what I'll show you some examples of next. But just before I get into some higher level questions, here's a quick summary of all of the double angle identities for you, and let's now take a look at some examples. So let's see if we can simplify 8 sine 3x cos 3x. Well, this looks a whole lot like sine 2a equals 2 sine a cos a. This part here is like our a, so a is very much like our 3x, and there's another a. And instead of 8, I really only wanted a 2, and that's okay, because I could factor out a 4 and think about this as 2 sine 3x cos 3x, or if it's easier for you, you can think about this as 2 sine a cos a, where a is 3x, and now I can use this double angle identity. So this part here in the brackets is really the same as sine 2a, and my a value is 3x, so I'll create some extra space here. So this is really sine 2 times 3x, which is 6x. So those are equivalent statements, or a simplification of 8 sine 3x times cos 3x. Here's another one for you. Let's see if we can simplify 2 cos squared 4x minus 1. So if you can identify that 2 cos squared a minus 1 is the same as cos 2a, then you can see that this part is really like your a value. And so this simplifies to cos double of 4x, which is cos of 8x. These can be a little tricky to see how they simplify. Again, if you can identify which equation looks similar, then you can start to do either a substitution or some algebraic manipulation, or both, and then you can actually apply and simplify last. Okay, let's take a look at how these things can be integrated into solving equations. So we're going to try and solve sine double angle of x equals tan x on 0 is less than or equal to x, x is greater than or equal to 0 or less than 2 pi on the interval from 0 to 2 pi. So as we did with other solving, let's change this to terms that we can work with a little easier, which is generally sines and cosines. So the only substitution for sine 2x is 2 sine x cos x, and tan x is the same as sine x over cos x. From here, you would notice that cos x has a restriction. It can't be equal to 0. So if I generate any of these solutions, when is cosine equal to 0? Right here and right here, that's pi over 2 and 3 pi over 2. If the rest of my work generates those solutions, I have to get rid of them. So that's part of the restricted domain. Then I can just start doing some algebraic manipulation. So on this side, maybe multiply by cosine. On this side, also multiply by cosine. I get 2 sine x cosine squared x is equal to sine x. Subtract sine x on both sides. To make it equal to 0 so that I can factor. And now I can split this into two parts. So sine x could be equal to 0, or 2 cosine squared x minus 1 could be equal to 0. Solving sine x is equal to 0 is, using the graph, fairly easy. I can identify that 0 and pi will be part of my solution set. Solving the other part, I need to make this equal to 1, divide both sides to get a half, take the square root, give me plus or minus 1 over root 2, and hopefully you can identify that that's a 45-degree angle. So when is it a 45-degree angle? When the reference angle is pi over 4, and it happens in all quadrants because it's plus or minus. So the solution set for this one will be pi over 4, 3 pi over 4, that's in quadrant 2. Down here will be 5 pi over 4, and 7 pi over 4 in the last quadrant. And so my grand total, since none of these 4 and none of these 2 are restrictions, I don't really even need those restrictions, and I can just list these out. I don't have to list them in order. Some people say it's really nice to, but I can just list out all of my solutions, make it visible so I can ensure that people know that's my solution set, and I'm done. A question for you is, how could you go about verifying that this is true? And if you can think of a way to verify that these solutions are actually the solutions to this equation, then go ahead and do that. If you aren't sure how you could verify that these solutions are true, then we'll chat about it in class. Just let me know. Okay, let's try a proof. Okay, so here's my proof. Let's set up the wall so that I don't cross over from one side to the other. And I would go ahead and change the tan 2x, because I happen to know that it can be, instead of tan 2x, it can be, oops, let's make sure I use the right one, 2 tan x over 1 minus tan squared x. And I don't really be wanting to work in cotans on the right-hand side, but instead of changing everything to sines and cosines, I can, it will work. I'm just going to change everything to tangents, and the reason that I'm going to choose tangents is because look at the left-hand side, it's all in tangents. So the top is 2 over tan x, and the denominator is 1 over tan x squared minus 1, and I don't like having denominators or fractions within fractions, so I'm going to multiply by 1, and my special form of 1 is going to look like tan squared x over tan squared x. If I do that on the top, one of the tans is going to cancel, and I'm going to get 2 tan x. And if I do it on the denominator, tan squared x cancels with tan squared x, I get 1 minus tan squared x times 1 is tan squared x. And look at that. I have exactly the same on both sides. So I'm done my proof. Okay, we'll see you in class.